Hello there. Thanks for joining this session. This is Nicholas Goodman. I'm a sales engineer at Solace. I am joined today by my colleague, Quang Nguyen Tien from Snowflake, and we're excited to tell you about some work we've been doing together on real-time data ingestion, taking data from Solace and piping it into Snowflake using their new Snowpipe Streaming API. A little bit of background real quick, and why are we doing this? We have many different approaches in the world for how we handle data. There's kind of this two-tiered approach, slow track, fast track, that we typically see in the world today, where we started in the past with databases, and as data got larger, as we moved into data warehouses and data lakes, we often require kind of local or snapshots of the data, operational data stores or master data management tooling on top of that. So our applications could maintain real-time status. Meanwhile, the data themselves became a little lower. As the CTO of Amazon famously pointed out at the recent 2022 reInvent Summit for AWS, the world is asynchronous though, and I'd be quick to point out in the real world, of course, it's also stateful. The real world is stateful. And so we would like to see that data is as real-time as our apps, and there's been many different approaches and ways to tackling that. And we commonly look at trade-offs, things like bulk efficiency, about how much data can we process versus latency, and are we doing real-time analytics using stream processing, or are we doing deep analytics on large databases? And what we see now is kind of, the goal is to kind of close the gap between this two-level or two-tiered view of the world and to bring more real-time capabilities to our proper large database environments. So what are some real-world use cases? One common example is real-time trade analytics that we see in capital markets, as well as some upcoming changes to what is known as trade settlements and reconciliation. There's a big push in the industry to move what is known as T+1, which means reconciling and settling all trades within a day. And then some other cases that we've seen from here at Solace, as well as from Snowflake, some real-time insurance policy verification. So not only does your applications need to be real-time, but you need real-time state. You need to know if something is active right now. As well as things like database synchronization, migrating from old databases to modern ones, and keeping your data sets in store, as well as certain manufacturing IoT use cases, where you want to take data from the field, analyze it in real time. For the uninitiated, I'm sure here at the EDA Summit, you may have heard of Solace before, but just a quick little introduction into our platform, as well as our recently released connector strategy. So fundamental is what we call the Solace Event Mesh. Solace Event Mesh is built up of a collection of brokers. So instead of point-to-point communication between applications and services, use brokered communications so that the apps themselves are now decoupled. Our broker does run as an appliance, a software image, or as a SaaS offering. And it basically runs wherever you want it to, whether that's on-prem or cloud and across different clouds. We do both pub/sub messaging paradigms as well as queuing paradigms with some fantastic guaranteed in-order message delivery, no message loss. The event mesh, on the other hand, is when you take multiple brokers, link them together, and the ability to dynamically route messages from point A to point B with built-in high availability and disaster recovery semantics. There's probably plenty of other talks in previous summits, as well as this one, that will go into more detail, but that's kind of what you need to know with regards to what we'll be doing here with Snowflake today. Now, in the past few months, Solace has also come up with a new connector strategy. We have for years had what are known as native protocol support, the ability for applications and services to talk to an event broker with many of our implemented protocols. We also have certain what are known as broker integrated connectors. The broker itself knows how to integrate to apps and services to the outside world, as well as what are known as external embedded connectors, something like the Kafka Connect, where external party can connect into our pub/sub broker. But what I really like to focus on is what our new connector strategy, known as self-contained connectors, are. These live as external processes or as Docker images, which connect an event broker to an outside service, whether that's a third-party database, a third-party queuing system, or other applications that we have yet to be developed. What are the benefits of the self-contained connector model? Is, well, one, there's a standard way that we deploy them. They're all built on a common library. And so it allows us to deploy them, or allows our customers to deploy them in a unified way. They have built-in monitoring management API, so they're RESTful. You can check on the statuses of their workflows and see what data is flowing from point A to point B. They're very heavily configuration driven. So you deploy the connectors, and with an application configuration file, you specify what your event source is, what your event target, and then any other settings that are related to that. And they have built-in high availability and scaling semantics as well, so that you can bring more connectors online, spin them up, spin them down dynamically as your workflows change. And it is one of these connectors which we will be talking about in just a moment. But now I would like to hand over the presentation to my colleague Kwong, who will be talking a little bit about Snowflake and their new Snowpipe Streaming API. Kwong?
Thank you, Nick. Yes, hi everyone. As Nick mentioned, I'm from Snowflake Professional Services. And yeah, let's dive deep into what Snowflake is and what we offer in regards to Snowpipe streaming. So Snowflake, as you probably all heard of, right? We've evolved from a cloud data warehouse into a data cloud platform, right? With many workloads, no data silos, equipped to mobilize your data, right, and power your workloads. And some of the workloads include, data collaboration, right, data sharing, data engineering, data science and ML, right, data applications where you can actually share your applications across a Snowflake ecosystem, on top of all these data warehouse, data lake, and Unistore platforms. So as a platform, we do provide many ways to ingest the data. And of course, one of them is Snowpipe streaming that we're going to talk about now. So what is a Snowpipe streaming? So Snowpipe streaming is really a low latency loading of streaming data row sets, right? Using the ingest SDK that we provide to our customers and your own managed application code. How does it kind of really work, right? If you kind of grab the Snowpipe streaming API, right, it's not intended to complement to replace Snowpipe, our original feature, right, that we call now Snowpipe files, but it's more of intended to complement it, right? You can use the Snowpipe streaming API in different streaming scenarios where data is streamed via rows rather than files. And then it fits into that ingest workflow that includes your existing custom Java application that produces and then receives different messages and records. The API pretty much removes the need to create any files to load into data and into the Snowflake tables. And it enables you, right, the continuous loading of these data streams into Snowflake as the data becomes available. So a little bit more of detail around the whole mechanism, right? So think of your Java processes, right? On-prem service, whether it's a Kafka cluster or a Solace broker, right? That maintains a stream, right? You create a streaming ingest client that is then used by N threads. And each of these threads then opens a channel. And the channel can be either against one single table or multiple channels can also go against that one single table. It writes a blob, right? And then on insert row, right, it calls this interstage that returns the acknowledgement, right? And it doesn't wait for the commit service. Commit service pretty much ingests these blobs, right, in the right order, and then the low latency is kind of satisfied, right, throughout the whole efficiency, and the data is available fast and immediate for the querying downstream. So when do we generally use it? Snowflake Ingest SDK, definitely when we need, or there's a requirement for near real-time latency data availability, right? It's very suitable for IoT, web logs, or micro batch ticker data. We just released manufacturing data cloud, and a lot of our manufacturing clients are using that for their operational data. And in order to kind of understand, right, the differences between Snowpipe files and Snowpipe streaming, right? Nick, can you go to the next one? The Snowpipe original file base, right, is pretty much designed for batch row sets as files, right? So if you are looking to ingest a large files, 10 million or 10 terabytes per hour, right? Snowpipe original file base is still something that we recommend, right? If the latency is pretty much less than a minute or around like 30 seconds, right? This is probably like the ideal way how to ingest your data. For Snowpipe streaming, it's really designed for row sets, so inserting your rows, right? So the amount of data is definitely smaller sets of data with kind of lower latency, but pretty much there's no need of any files, and the latency, if you think of less of 5 seconds, that would be your ideal use case for streaming.
Fantastic, thank you, Phong. And so now we're going to talk about how Solace has built a connector using the new Snowflake Streaming API, and kind of what the overall architecture looks like. It's quite similar to what was just introduced, and what are some of the little nuances about the Solace approach. As Phong mentioned before, a particular channel on the Snowflake side, what is known as a Snowpipe streaming channel, feeds only an individual table, but multiple channels can feed a single table. So in the Solace world, our record of store is known as a queue. Publishers publish to topics, and queues can attract topics. And so data can come from multiple publishers and be inserted into a queue. It could be one-to-one, it could be many-to-one, through a feature known as topic-to-queue mapping. But from here on out, essentially, it's a one-to-one-to-one relationship. And so when we define our connector workflow, we define the source as being the queue that the data is coming from, and we define the destination as the table in which the data is going into. The Snowflake connector in itself is essentially stateless. While it's up and running, assuming things are going well, it does internally buffer the data so that we can take individual messages that come off of Solace queue and micro batch them into the table. That's done for performance reasons. But essentially, you can think of it as a one-to-one mapping between a queue and a table, or in cases where you want to insert rows a little bit more performantly, you can have multiple queues feeding a single table. I talked a little bit before I said the phrase, a guarantee an in-order delivery. That's a characteristic feature of Solace. And so we'll take a look at how that looks for a connector in the connector world, because now instead of just having a broker and an application that's talking to it, we have an intermediary, a third party kind of hop that the data has to flow through. When the connector first starts, it begins pulling data off of the event broker, and it can do one message at a time, but typically, like I said, for performance reasons, we'll buffer them up in what is known as a micro batch. And then once we've reached either a timeout or a set number of messages, we'll insert those rows into the Snowflake channel. Now, Snowflake now just kind of takes it and does its own thing. Behind the scenes, now it is taking those rows that I've inserted, adding them to the table, and they are processed as they were received. The connector then polls the channel and says, hey, what was my last committed offset token? The offset token is a piece of information you add when you do the insert. And Solace messages do have what is known as a monotonically increasing message ID, similar in the Kafka world to an offset. whereby we can say that a particular message is newer or older than another. So we'll pull the channel for the last committed offset token. And once we determine that the particular batch has been committed, we will then acknowledge back to the broker that it is safe to delete those messages from the queue. Now, if you're a keen observer, this is what is known as at least once message guaranteed practices. There is a small edge case here, which is that what happens when messages have been taken from the queue, inserted into the Snowflake channel, but say something goes wrong with either the network or the connector crashes for some reason. We are now left in a state where this at least once message guarantee can result in multiple deliveries, because the data still lives on the queue and will be redelivered the next time the connector comes online. So we have built-in data deduplication logic inside the connector. So in this scenario here, we have a sample where 2 messages have been previously processed. They were successfully inserted into the table, but they are still sitting on the Solace event queue. We actually start the connector by asking the channel, what was your last committed offset token? And we'll notice that 2 of the records on the queue are older than the last committed offset token, or older or equal to. When the connector begins, it'll start pulling messages off the broker, determine that the messages it got are now older than the last committed message, and delete them as they are received. And once it sees a new message, it'll resume its normal behavior, start buffering those up into the in-memory buffer, push them over to the Snowflake channel, and message continues as before, where we then pull the channel for the last committed offset token. And once we've reached the batch offset, we will commit the entire batch at once, now deleting the previously consumed records as well as the new records that have just freshly been inserted into the table. Some notes on performance, in case you're wondering. We did talk about this is like a real-time system. There are plenty of knobs to turn when configuring a Solace connector. One is, well, what's the batch size? So increasing the batch size is great for increasing throughput, but it does add latency, of course. And so we do have but 2 different settings. How big is the micro batch supposed to be? And how long do we want to wait before pushing those messages over to Snowflake regardless? Likewise, there is part of the system is poll-based, namely when you're checking what the last committed offset token is, that is done on a polling interval. That's also configurable, as well as the option to only process a single batch at a time or process multiple batches at a time. Typically, you do multiple batches at a time if you want to increase both latency and decrease latency and increase throughput. And then, of course, there's your how do you deploy, right? So we do see this as a 3-party system. You have the broker, the connector, and the database itself. All of them can live in the cloud. And if we're just talking about performance, performance is greatest when all 3 live in the same deployment region. However, from a resiliency consideration perspective, in the real world, if your source data system is not living in the cloud or it lives in a different region in the cloud, the broker tends to live next to where the data source is, and the connector will live closest to the database in terms of deployment regions. Haven't done extremely thorough testing on our performance characteristics of this connector yet, so I'll call this some napkin math. Using my personal laptop here, I was able to run a on laptop Solace broker as well as the connector instance, and using a single queue and a single workflow to an AWS US East 1 Snowflake table from a home internet connection, I'll add, was very easily able to achieve 10,000 rows inserted in a period of only 2.8 seconds. That's 3,500 events per second, and that's just in a home office setup. So she's pretty fast. Now I'll do a very brief live demonstration. I put together a very simple HTML5 web application. This is using our Solace Sol Client JS, our Solace SDK for JavaScript. The application will track some touch movements, publish the coordinates to an event broker, which will then get queued up, consumed by the Snowflake connector, pushed into a table on Snowflake, and if all goes well, we'll see it on a nice Snowflake dashboard. We'll see here on the top left, I have my web application, And I will hopefully be able to get some data in here. And I want to say to everybody who joined today, thanks for watching. And we'll see here, all messages have been committed and act. And let's go ahead and refresh our query. And all going well, we got our data live into a Snowflake table. This concludes our presentation. I thank everybody for joining.